Hello, and welcome to the lecture on 7.1. Today we're going to talk about trigonometric identities. And we're going to start with a definition of what an identity is, but in order to do that, we need to know what an equation is first. An equation is a statement that two mathematical expressions are equal. Basically, it's just a statement with an equal sign, and you have expressions on each side of the equal sign. An identity is an equation that is true for all values of each variable. Now, what this means is sometimes when we have an equation, we might have something like this: x plus 3 is equal to 4. And we're solving for x. This is an equation. An expression here, x plus 3, and an expression here that's 4, and they're equal. So this is an equation. This is not an identity, because this is not true for every value of x. You can simply plug in x equals 0 for x, and you can see that this is not true. Now, an identity is something different. So an identity might look something like this. A squared minus b squared is equal to a plus b times a minus b. And no matter what I plug in for a and b, this will always be true. This is the difference of squares factoring formula. This is an identity. A trigonometric identity is an identity that involves trigonometric functions. So we've already seen a few trigonometric identities, specifically the Pythagorean identity. Sine squared theta plus cosine squared theta is equal to 1. This is the trigonometric identity. It's true for any value theta. Now this is what we want to work with, these types of equations, these identities. Now we've already covered a few fundamental trigonometric identities, so let's go over those really quickly, and then we'll move on to some new stuff. Fundamental trig identities. Now, we can start with the Pythagorean identities, but I'm going to start with the reciprocal identities. These ones are the reciprocal functions, the reciprocal trig functions. So we have that cosecant of x is equal to 1 divided by sine of x. This is a reciprocal identity. Similarly, secant of x is equal to 1 over cosine of x. Cotangent is equal to 1 divided by tangent of x. And we often put in tangent and cotangent. Tangent of x is equal to sine over cosine. And cotangent is equal to cosine divided by sine. Now, these are not technically reciprocal identities, but we often lump them together with the reciprocal identities. Now, probably the most important identities are the Pythagorean identities. Here, the one that everyone needs to remember, sine squared of x plus cosine squared of x is equal to 1. This one is the most important Pythagorean identity out of the three. It's also one of the most important identities. I won't say that it is the most important, but it is probably the most important up to this point. The next Pythagorean identity is 1 plus tangent squared of x is equal to secant squared of x. And lastly, cotangent squared of x plus 1 is equal to cosecant squared of x. These are the three Pythagorean identities. We've covered them already pretty extensively, so I'm not going to go into how we prove them again. We have new identities, your even and odd identities. Recall, a function is odd when f of negative x is equal to negative f of x. And a function is even when f of negative x is equal to f of x. So here what we're saying is if we have a negative input, then we can pull that negative out for our odd functions, for any odd function. Even is a little different. The negative on the input doesn't change the function at all. If we have a negative input, it's the same as if we didn't have that negative at all. Now the identities are that sine of negative x is equal to negative sine of x. Now, does this make sine even or odd? And you should say odd because we have a negative sign of x here. So sine is an odd function. Tangent is also odd. Tangent of negative x is equal to negative tangent of x. Now cosine is an even function. So cosine negative x is equal to cosine of x. This also means then that cosecant is odd, cotangent is odd, and secant is even because they're the reciprocals of sine, tangent, and cosine respectively. Right, next I want to introduce some new identities, the cofunction identities. You might be wondering what the relationship is between sine and cosine, secant and cosecant, and tangent and cotangent. This is where they're related, the cofunction identities. Specifically that sine of pi over 2 minus x is equal to cosine of x. Tangent of pi over 2 minus x is equal to cotangent of x. And secant of pi over 2 minus x is equal to cosecant of x. Similarly, cosine of pi over 2 minus x is equal to sine of x. Cotangent of pi over 2 minus x is equal to tangent of x. And cosecant of pi over 2 minus x is equal to secant of x. Now these can be easily shown simply by using a graph. You know how to shift graphs. So if you take your sine graph and you shift it by using this manipulation, pi over 2 minus x as an input, then you'll get cosine of x. So we can show each of the cofunction identities in this way. And I'm not going to prove it. If you want to do it on your own, feel free. What I want to talk about next is simplifying expressions. Now, in order to simplify an expression, we want to write an expression in a different form. Now, in order to do this, we need to use identities because they're going to be true. Identities, remember, are true for every value that the variable can take. So we don't want something different. We just want it to look different. We want the value to be the same, but we want it to look simpler. Let's do an example here of what I mean. Let's look at sine of u plus cotangent u cosine u. Now, a lot of times when you're trying to simplify these expressions, you're going to want to change everything into sines and cosines. And in this case, it'll be actually really beneficial. This might look a little bit complicated, but it's actually not. What we're going to do is we're going to use identities that we know in order to manipulate how this looks. For instance, remember, cotangent of theta is equal to cosine of theta divided by sine of theta. So I can replace this cotangent of u with cosine of u divided by sine of u. So we end up with sine of u plus cosine of u divided by sine of u times cosine of u. And I'm going to say that this is divided by 1 because it's the same thing. Then we can multiply these two. So we have cosine of u times cosine of u, and we get cosine squared of u. Okay, so it doesn't look much simpler yet. So now we have this, sine of u plus cosine squared u divided by sine of u. Right, now the next thing that I want to do is I want to combine these two things. I want to combine these two fractions. Now in order to do that, I need a common denominator. Right now my denominator for my sine u is just 1, so I need to multiply top and bottom of this quote-unquote fraction by sine of u. So we multiply by sine of u over sine of u. And remember that sine of u is divided by 1. So when we do that, we end up with sine squared u over sine of u plus cosine squared u divided by sine u. Now, I can combine them because I have a common denominator. So we end up with sine squared u plus cosine squared u divided by sine of u. Now, again, this doesn't look much simpler than what we had before, except now you might recognize sine squared u plus cosine squared u is an identity that we know. Specifically, sine squared theta plus cosine squared theta is equal to 1. Now, this is true for any value theta. Even if theta is u, we get sine squared of some angle plus cosine squared of the same angle is equal to 1. So we can replace this sine squared plus cosine squared with 1, and we end up with 1 divided by sine of u. And then 1 over sine of u can be rewritten as cosecant u. And we're done. Now this is clearly much simpler than what we had to start, but it's the same exact value. Try one on the accompanying worksheet. Simplify the expression. Cosine squared theta times 1 plus tangent squared theta. The next thing I want to talk about is proving identities. This is the same as simplifying an expression, except there's a given endpoint. So when we prove an identity, start with one side. We want to convert this side to the other side without changing its value. What we want to do is we want to change the form of the expression into the other form. So we assume that it's true, and we try to show it by changing its form. We use known identities to achieve this transformation. Recall that identities are true for every value each variable can take. So that's what I mean by we start with one side and we convert to the other side without actually changing the value. When we use an identity to change its form, we're not actually changing the value because they are equivalent. We use an identity because it's equivalent for every possible value each variable can take. A helpful hint. If you get stuck, change trig functions to sines and cosines. So wherever you can, wherever it's possible, it's often a good idea to change everything in terms of sine and cosine and simplify from there. That usually helps. Let's do an example of proving an identity. Now this chapter is actually going to deal a lot with proving identities, so you want to get these down early if you can. So suppose we have this. Cosine of x times secant of x divided by tangent of x is equal to cotangent of x. Now, we might not know if this is actually a true identity or not, but we have to assume that it is, and we try to get from one side to the other. And I'll go over how to disprove an identity, a quote-unquote identity, in a bit. But for right now, we're going to go ahead and just prove this identity. This is actually an identity. So we start with one side. Generally, you want to start with the more disgusting looking side. And in this case, obviously, it's the left side. So we start with the left-hand side, which is cosine of x times secant of x divided by tangent of x. Okay. Now, we don't write the right-hand side. We just write the left-hand side, and we try to manipulate this in some way in order to change the form of this expression. So here what I'm going to do is I'm going to change secant into 1 over cosine. Because remember, secant of x is equal to 1 over cosine of x. So here we would end up with cosine of x times 1 divided by cosine of x divided by tangent of x is what we're left with. Now we can see here that we have cosine times 1 divided by cosine. So these two actually cancel because you're both multiplying and dividing by cosine. So we can just cancel these. And this is then equal to just 1 divided by tangent of x. Now you also want to keep in mind, and you'll get better at it with more practice, but keep in mind your end goal. We want to get to cotangent. So is there any way to get from 1 over tangent of x to cotangent? Yeah, in fact there is. Cotangent is exactly 1 over tangent. So we can go straight to the end. This is cotangent. Because we have the reciprocal identity, 1 over tangent is equal to cotangent, we can go straight to the end. So now we've shown that this is equal to cotangent. Granted, it's equal to this expression, and this expression is equal to this expression, and this expression is equal to this expression. So it's actually connected to cotangent of x through a couple of links in a chain, but it doesn't mean that it's not equal. It actually means that it is equal. But it still means that it is actually equal. So cosine secant divided by tangent is equal to cotangent. Now I want to mention a couple of things. First, we're going to talk about disproving identities. Disproving an identity is as easy as finding a counterexample. Really, all we need to do is find one case for which the quote-unquote identity doesn't actually hold, because I want you to recall an identity is an equation that is true for all values of the variable. So here, we're going to show you how to disprove an identity, a quote-unquote identity, obviously. So here, let's say that we have sine of x plus cosine of x is equal to 1. Now, you might not be able to immediately see that this is not an identity, but we can show that it's not an identity. We just need to figure out an x value for which this is not true. And we can start with some easy ones. Let's say x equals 0. Well, if x is equal to 0, then cosine is equal to 1. Sine is equal to 0. So x equals 0 actually works, unfortunately. This doesn't provide us with a counterexample, so we need to continue. Let's try pi over 2. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. So we'd have 1 plus 0, which is equal to 1. So again, this does work. Now let's try x is equal to pi. Sine of pi is 0. Cosine of pi is negative 1. Now negative 1 is not equal to 1, so we can see that x equals pi does not work, which means that this is not an identity, because we found an x value for which this quote-unquote identity doesn't hold. So it's not actually an identity. Now I do need to make a note here, because it is very important that you do not try to prove an identity in this fashion. You can't prove an identity by exhaustion, meaning you can't just start plugging numbers in to an identity and say, oh, well, it worked for every number that I tried, therefore it's true. That's not the case. As you can see, I have one that is not an identity, and I already tried 2 values. If I stopped after the second value and I said, well, you know, it worked for these 2 values, therefore it works for all the values. That's not the case. If you're going to disprove an identity, you can do it this way, because you just need to find one case for which this quote-unquote identity doesn't work. But if you're to prove an identity, you need to do it the way that we did before, where we start with one side, and we continue to link together a sequence of expressions to get to the expression that we want. And we use identities that we know in order to do that. So I will repeat, because there are too many students that mess this up. You cannot prove an identity by testing points. It is impossible. You would have to test literally every single value, because an identity is an equation that's true for all values, which would mean you'd have to test infinitely many x values in order to prove an identity, which is obviously impossible. Do another example here. Combining fractions. So let's prove an identity by combining a couple of fractions. Now, the identity that we're going to prove is that 2 secant of x is equal to 1 divided by secant x plus tangent x plus 1 divided by secant x minus tangent x. Now remember what I said before. When we're trying to prove an identity, you want to start with the side that looks worse. In this case, that's going to be the right-hand side. Left-hand side is pretty nice. It's easier to work from something that looks ugly to something that looks nice instead of trying to go the other way. So let's start with the right-hand side here. Our right-hand side is 1 divided by secant x plus tangent x plus 1 divided by secant x minus tangent x. Now, first things first, I'm going to multiply top and bottom of each fraction by something that's missing in the denominator. Essentially what I mean is that we need to find a common denominator so that we can add these two fractions together. Our common denominator is going to be secant x plus tangent x times secant x minus tangent x. Like this. So, notice this fraction is missing secant x minus tangent x. So let's go ahead and multiply top and bottom by that. And then the right fraction is missing secant x plus tangent x. So we multiply top and bottom by that. Now what's left on top here, because it's 1 times secant x minus tangent x, in the first fraction, we have just secant x minus tangent x. And in the second fraction, the top is just secant x plus tangent x, because again, secant x plus tangent x times 1. And then we have a plus in between, so we have secant x minus tangent x plus secant x plus tangent x. So plus secant x plus tangent x. Okay, now we can simplify a little bit. We have a negative tangent and a positive tangent. These two cancel. So we end up with 2 secant on top. So 2 secant x. Now, in our denominator, we have a difference of squares. I also want you to notice that the end goal is to get to 2 secant x. So this denominator, we can expect to go to 1 somehow, because we have 2 secant x in the numerator, and if we had 2 secant x divided by 1, we would be done, because that's what we want to get to. So let's FOIL out the denominator, and we get secant squared x minus tangent squared x. This isn't exactly something we've seen before. It's close, but it's not exactly something we've seen before. I want you to look at this identity. 1 plus tangent squared x is equal to secant squared x. So we have an identity that deals with tangents and secants, even squareds, tangent squareds and secant squareds. But we don't have this identity exactly. We have secant squared minus tangent squared. So if we manipulate this one a little bit, and we just subtract the tangent squared over, we would have 1 is equal to secant squared x minus tangent squared x. Or, if you're more comfortable, you can take your secant squared here and substitute 1 plus tangent squared. So if we said secant squared is equal to 1 plus tangent squared, we would have, this would become 1 plus tangent squared minus tangent squared, and you'd just be left with 1. Or you can manipulate the identity that we've known by just subtracting tangent squared over, and you have 1 is equal to secant squared minus tangent squared, which is exactly what we have in the denominator here. So we then get just 2 secant x divided by 1, because secant squared minus tangent squared becomes 1. Which is exactly what we wanted. We finished because we have 2 secant x, 2 secant x. We're done. That's all we needed to do. I will note that it does help to label your steps. So here, multiply, I might say on the right-hand side that I multiplied top and bottom by secant minus tangent and secant plus tangent. And then here, FOIL out the denominator. I would label something like this. And then this one would be use the identity. Once I use this identity, then I got to the endpoint, and that finishes out the problem. Okay, let's do one more example. Don't worry if you don't get these right away. These problems take a while to actually understand and get through. Many students have trouble with these, so if you're not getting it right away, it's okay. You just need a little bit of practice. So let's prove or disprove the identity. And we're going to do this by introducing some extra expressions. So our identity is 1 minus cosine alpha divided by sine alpha is equal to sine alpha divided by 1 plus cosine alpha. Okay, now, both sides are equally disgusting looking. I'm going to start with the left-hand side. Generally, we start with the left-hand side if both of them are equal. Also, I will note that the left-hand side I think is a little bit easier to deal with. Not much easier, but a little bit. So left-hand side would be 1 minus cosine alpha divided by sine alpha. Okay. Now, what can we do with this to get closer to this, the expression that we want? Well, there is a trick that we use a lot, and that is to get a difference of squares, especially with the Pythagorean identities, like I did in the previous problem. We FOILed this out, and we had a difference of squares. Except with the sine and cosine Pythagorean identity, we always have 1 minus cosine or 1 minus sine, and we can create a difference of squares by multiplying top and bottom by the missing piece of the difference of squares. So what I'm going to do is I'm going to say that we multiply by 1 plus cosine alpha, top and bottom. Now when I multiply top and bottom by this expression, I'm actually not changing the problem. Why am I not changing the problem? It seems like I'm changing the problem. I'm multiplying top and bottom by something. Why is this not changing the problem? When I say changing the problem, I mean, why is this not changing the value of the problem? It's only changing the form. Well, if you remember, 1 is the identity, the multiplicative identity. And here, 1 plus cosine alpha divided by the same thing is exactly 1. It's just a unique form of 1. Something divided by itself is equal to 1. So I'm multiplying this expression by a factor of 1. And because we're multiplying by 1, we're not changing anything because 1 is the multiplicative identity. It doesn't change anything when you multiply by 1. So on top, we can FOIL this out, and we get 1 minus cosine squared alpha. And on bottom, we don't need to multiply the sign in, just leave it on the outside. That's another trick that you'll pick up, is that you don't always want to distribute an expression. So now we have 1 minus cosine squared alpha. Now here, we just FOILed. And here what I'm going to do is I'm going to use the identity sine squared alpha plus cosine squared alpha is equal to 1. I'll show you what I mean over here though. So we have 1 minus cosine squared alpha. If I subtract my cosine squared over, then I have exactly sine squared alpha is equal to 1 minus cosine squared alpha. And that's exactly what we have. So I can substitute 1 minus cosine squared alpha with sine squared alpha. So we end up with sine squared alpha divided by sine alpha times 1 plus cosine alpha. And as you can see, hopefully, we have 2 signs on top and we have 1 sign on bottom. So we can just cancel one of the signs on top and the one in the denominator. And we just end up with sine alpha in the numerator and 1 plus cosine alpha in the denominator. And we're done, because this is exactly what we wanted. sine alpha divided by 1 plus cosine alpha. Sine alpha divided by 1 plus cosine alpha. So we're done. We've shown that this is equivalent to this by using these links in a chain, these expressions. Go ahead and try one on the accompanying worksheet. Prove the following identities. Secant theta minus tangent theta is equal to 1 divided by secant theta plus tangent theta. And the second identity I want you to prove is 2 cosine squared theta minus 1 is equal to 1 minus 2 sine squared theta. So these are separate problems. I give you two because this topic is actually a challenging topic to learn, so more practice is always beneficial. Next thing I want to talk about is trig substitution. Now, I'm going to note here, there are 3 forms of trig substitution. Specifically, a squared minus x squared. A lot of times a squared will just be 1. So just keep that in mind. X squared minus a squared and a squared plus x squared. When we use trig substitution, what we're doing is we're assigning x to be a trig function. Now, picking that trig function depends on the form. We have a negative x squared, a positive x squared, and a negative constant squared, and then we have a constant squared plus a positive x squared. Now, each of these takes a special function. Here, for the first one, we substitute x equals a sine. And you want to change your variable, so we use theta instead of x. And I'll explain to why we do this in a second, but for the second form, we do x is equal to a secant theta. In the third form, x is equal to a tangent theta. Now, you might notice that this will give us something that's related to the Pythagorean identities. And if you did notice that, great, because that is exactly what we're doing. These substitutions are informed by the Pythagorean identities, specifically sine squared theta plus cosine squared theta is equal to 1, and 1 plus tangent squared theta is equal to secant squared theta. Now, this first one, we have a squared minus x squared. Really what we're doing is we're subtracting this sine squared over, so we would have cosine squared is equal to 1 minus sine squared. We'd have a quote-unquote 1 minus sine squared. That's the idea. In the second one, we would have to subtract the 1 over, so you would have a secant squared minus 1. And in this one, you leave the 1 and the tangent on the same side, so you have 1 plus tangent squared. I'll show you an example of this because choosing the form is very important. Let's do this example here. Substitute x is equal to sine theta and simplify. Where 0 is less than theta is less than pi over 2. We don't need to worry about that for now. So if our expression is 1 minus x squared divided by x, and we're substituting x is equal to sine, I want you to notice that it'll follow into this Pythagorean identity. So if we let x be sine theta, we plug that in, we get the square root of 1 minus sine quantity squared, so squared theta here, divided by sine theta. Okay. Now, how do we simplify this? Well, it's exactly how I told you. We had the identity, sine squared theta plus cosine squared theta is equal to 1. Now, if we subtract the sine squared over, we would have cosine squared theta is equal to 1 minus sine squared theta. Now, notice 1 minus sine squared theta, 1 minus sine squared theta. So we have exactly the right-hand side of this identity. So we can substitute cosine squared theta. So we replace 1 minus sine squared theta with cosine squared theta. So this will become the square root of cosine squared theta divided by sine theta. Now, as you may know, the square root of a square, especially when theta is positive, or the cosine will give us a positive value, we end up with cosine theta divided by sine theta, which is equal to cotangent theta. And we're done. So we substituted in sine for x, and it simplified down to cotangent theta. Now this skill seems out of place in this section, but it's because it'll come up again in calculus. So they're just trying to prepare you a little bit for calculus. I want you to go ahead and try one on your own. Substitute x is equal to 2 tangent theta, and assume 0 is less than or equal to theta is less than or equal to pi over 2. Again, this is just to make sure that we have a positive value outside of our trig function. If our expression is 1 divided by x squared square root 4 plus x squared. Yes. Now I will note that you're substituting 2 tangent theta, so it'll very closely follow the previous problem, but when you get to this point where you plug in 2 tangent for your x here, your x squared, you're going to end up with 4 plus 4 tangent squared. Do not forget to square the 2 and the tangent. And then you want to factor that 4 out. And that's all I'm going to give you, which is pretty much the entire problem. All right, that will be it for today, and we'll see you all in the next lecture. If you enjoyed this video, please like and subscribe. All try one problems are on a worksheet linked in the description. The answer key and solutions are also linked in the description. If you want some free help, you can find me at twitch.tv/SkinnerPrincipal. Link is in the description, as well as my Discord server.